Hi everybody, welcome back to the channel. In this video we're going to take a look at something called integration by substitution. And what this is going to do is it's actually going to undo the chain rule. Now we're not going to necessarily undo the product rule and the quotient rule in this semester. You'll see that in Calc 2. But when you think about substitution or integration by substitution, what I want you to think about is that this undoes the chain rule. And so let's take a look at the chain rule and remember kind of where this comes from and see if we can kind of work backwards in this process. You might remember that the chain rule says start out with something like f of g of x. You have a function inside of a function and take the derivative of that whole thing. And when you do that, you get something like f prime of g of x times g prime of x. So to work backwards in this problem, what we're going to look for is we're going to look for something that originally starts with an f prime of g of x, where the derivative of g also shows up on the outside, and then we're going to try to work backwards. So let's look for, instead of calling this f and g, I'm going to look for kind of an outside function and an inside function. Here's what we're going to do. We're going to start out by looking for an inside function. So I'm calling them f and g here, but think about outside and inside function. G is an inside function here, whose derivative also shows up in the problem. So you have g of x and then you have g prime of x. Both of those need to show up in the problem in order for us to have this. Now sometimes it's a little bit tricky to see, but they're both going to show up there somehow. So what is g of x? And then the outside function is going to be the f prime that you have there. Now the idea of being able to undo both the outside and the inside functions here, we're going to use something called substitution. Some books will call it a U-Substitution just because U is a variable that we typically, or a letter that we typically use for the substitution here. But what we want to see is where do we have a function on the inside whose derivative also shows up on the outside. Let's take a look at an example first. I think it'll help kind of illustrate this. We could have something like the integral of 2x times the square root of 1 plus x squared dx. Okay, so remember what we're looking for is, do you have a function somewhere on the inside whose derivative also shows up? If you know what your inside function is, that's what we're going to call g. Okay, and what we want is, do we have that derivative show up? So if we know what g is, can we then go find g prime, and does g prime show up in the problem as well? So I don't know if you have any inclination here about what the inside function would be, but when you do a couple of these, it should hopefully be pretty clear, pretty straightforward, that g, the inside function, is 1 plus x squared. Usually parentheses are a pretty good giveaway of what's an inside function. There's no parentheses in this problem, but hopefully the inside is what's under the square root here, and that's not a problem. So what's inside is under the square root, that's 1 plus x squared. G prime would be 2x. Now, it's nice because not only is it 2x because 2x shows up out here, but just take the derivative of g. Some people try to say, oh, whatever's out here must be g prime. Not necessarily. Sometimes it can be different by a little bit. So just take the derivative of whatever g is, and does that show up in the problem there as well? Okay, so here's how we're going to deal with this. And by the way, this would mean that f prime, the outside function, is actually a square root function. Now notice I haven't put f prime of x because it's not f prime of x. It's really f prime of g of x and then the square root of g of x, but that's our outside function. So here's what a U-substitution is going to look like. This process of substitution is going to undo this chain rule every time, but it's a little bit of a new process for us. So let me go back to the beginning here. We have the integral of 2x times the square root of 1 plus x squared dx. Now I pointed out kind of what f and g prime were, just to say that those show up in the problem, just to know that we should be using this integration by substitution in the first place. But that doesn't tell us how to use it. That just tells us how to know when to use it. So here's what we're going to do. We're going to, instead of calling the inside function g of x, or instead of calling it inside, we're going to call that u. This is mostly just to be consistent with a lot of other books that all use kind of the same letter here. It's kind of like using x as our main variable all the time. U is commonly used as this inside function. So u is going to be 1 plus x squared. Okay, now go ahead and take the derivative of both sides of this equation with respect to x. In other words, find du dx. Now I know you could call it u prime on the left side, that's fine, but you'll see why I'm calling it du dx in just a second. So take the derivative of both sides. The derivative on the right side is just 2x. Okay. Now, do you remember when we talked about differentials back in the past, and we'd say get dy all by itself? Okay, the reason why I'm using du dx instead of just calling it u prime is because we want to be able to kind of get it so that we have dx separated from the du. So think about like when we found differentials and get du all by itself. So go ahead and solve for du. Du is 2x times dx. Okay. Now notice there are some pieces in these problems that show up, or in these equations here, that show up in the original integral. In fact, the 1 plus x squared, that's what u was. And then we have a 2x and a dx that show up in there, and those two together, 2x times dx, are equal to du. Now I will say this, sometimes students have a hard time seeing what to be able to substitute. So here's my recommendation for you. If you have, because here's what we're going to do. We're going to say, oh, this is the same thing as the integral, where you have the square root of u, and then 2x times dx, those combined together, those are du. So we're going to actually replace the 2x dx with a du. But if that is confusing, thinking about trying to replace all those together, here's my recommendation for you as just kind of a starter tip. You don't need to do this every time after you've practiced this a bit, but just as a starter tip, what I might recommend is this. Take the 2x dx, those are the things that are together in the du equation, and just move them all to the end. So rewrite the problem. Before you take any antiderivatives, before you deal with this, just move the pieces to the end. Move the 2x to the end so that it looks like this. All you did was just kind of swap things around using the commutative property because you have multiplication inside here. So you just put that 2x dx on the end. Now 2x dx is equal to du, so go ahead and replace 2x dx with a du. And go ahead and replace the 1 plus x squared with a u, so we get the square root of u right here. Now, this one should be a lot easier for us to integrate. Okay, and by the way, another way to write this is to write this as not u to the 1/2, but you have a lot of experience with this now. You know this is u to the 1/2, not the square root of u. So now you should be able to take the antiderivative here, where let's see, if you add a power of 1, because this is a power rule now, you should get u to the 3/2. You need a fraction down in front that's going to cancel out that fraction that would move down front from the power rule, and then don't forget that you need a plus c as well. Okay, so now we're trying to basically take our problem from the beginning that's a lot more complicated and turn it into an integral that's a lot easier for us to be able to handle. So this is what we get now at this point. We're almost done. But the problem is we have a u in the problem, and the original problem didn't have a u in it. The original problem had an x in it. So we should really go back and substitute back in. We substituted to go from x's to u's. We really should substitute backwards to go from u's to x's at the end after we've taken the integral. So really our answer at the end shouldn't be 2/3 u to the 3/2. It should be 2/3 times 1 plus x squared to the 3/2, because that's what u was, and then don't forget that plus c on the end. Okay, so we got to be careful about what's the inside function. Just to recap, we're going to call that inside function u. We're going to take the derivative of u, because hopefully that derivative is something that already showed up in the problem. And then we're going to get du by itself. Now we can't just replace a u, or we can't just replace an x with a u without replacing a dx somehow with a du. Here's what I mean by that. You can't replace something with a u in it and have had something like this while still having a dx on the end. That doesn't really make any sense. If you're going to replace a u, then you need to have replaced a dx and have a du on the end. So there's actually two different places where you're substituting. Once for the u equation and once for the du equation. And then once you take an integral of something that's a little bit easier, then you can work through and be able to substitute back in at the end and get x's at the end for your final answer. Okay, so the idea, let's take the inside function, find its derivative, replace the function with a u, replace the other function with something with a du. Hopefully that should give us something that's much easier to integrate. Go from there. let's take a look at another example. So let's say we have something like the integral of x to the third times the cosine of x to the fourth plus 2 dx. Okay, so again, we're looking for an inside function, that's what we're going to call u, whose derivative shows up on the outside. Now this one's a little bit different because the derivative of x squared, or x to the fourth plus 2, the derivative is 4x to the third. So you might say, do we have a 4x to the third showing up on the outside? Not quite, not exactly. We have an x to the third, but not the 4x to the third. So you can either have the derivative show up on the outside, or you can have something where your derivative is off by a coefficient, basically. If you have the same power, but you don't have that 4 out in front, that's okay. We're going to be able to account for that somehow. So we basically have, we almost have exactly the same thing as the derivative showing up on the outside. Not exactly, but we'll see how to handle that. So we're going to take u as being what's inside of the parentheses here. That's going to be x to the fourth plus 2. Now do what we did last time. Let's take the derivative of both sides. This is du dx on the left, and then take the derivative on the right side. That's 4x to the third. Okay. Now again, what I'm going to do is I'm going to replace, or just rewrite the original integral. I'm going to write it like this. I'm going to say this is the integral of cosine of, it's going to end up being the cosine of u, and then times, if I were to move the x to the third times the dx on the end, and move that all together on the end like we did originally, I want to be able to put something there that replaces the x to the third dx. Well, let's solve for du in the du dx equation. So get du by itself. This is going to look like du equals 4x to the third times dx. The problem is I don't want a 4x to the third dx, I only want the x to the third dx. So go ahead and divide both sides by 4 and move the 4 over to the other side, since we don't really want that on the right side, we want it there on the left. So this is going to look like 1/4 du equals x to the third dx. Well, x to the third dx is what we wanted up there. So now I'm going to replace the x to the third dx, but not with just a du. I'm going to replace it with a 1/4 du. Okay, so sometimes we're off by a constant, and notice what happens. Remember, we were off by a constant of, or a coefficient of 4, because we wanted a 4x to the third. We only had an x to the third. We're going to end up with a 1/4 in there to kind of cancel that out. It's kind of like undoing a power rule, basically. Okay, now the nice thing about integrals is that when you have this coefficient here, okay, even though that's kind of on the end right now, you can move that all the way to the front, and another way to write that is 1/4 times the integral of cosine of u du. Okay, so this is kind of nice because now the integral on the inside, the integral is just the cosine of u. That's a lot easier than the integral that we started with at the beginning. If you think about how to undo the cosine of u as a kind of taking an antiderivative there, you should get 1/4 times the sine of u, and then don't forget plus c. Now I'm going to go ahead and put the whole thing sine of u plus c here in parentheses with the 1/4. It's a little bit semantics here. It doesn't really make that big of a difference in this case where they have parentheses, because if you were to distribute the 1/4 here and you get 1/4 times c, that just means c is a different constant on the end than what you would have had originally, but it's still just a constant on the end. So c is just a placeholder for some constant. You would have ended up with a different constant, but that's okay. All right, so either way, I'm fine with you writing it like this, or you could have written it as 1/4 times the sine of u plus c. Either way, it's just these two c's are technically different, like that. Okay, and then go ahead and replace a u with what u is originally equal to. Okay, so you should end up getting a result like 1/4 times the sine of, let's see, u was x to the fourth plus 2, and then plus c. Okay, so that's what we originally, that's what we get as our integral there. And again, this is an indefinite integral. You can do the same thing with definite integrals. Then you just have to get to the end, have an x value of a and b. Again, plug those in, subtract, just like we did before. Okay, I hope you enjoyed.